talking about momentum. Physicists like to call it the quantity of motion.
So, let's start with a question and get you thinking. Picture this. A massive truck is just rolling along slowly, and right next to it, a cyclist is speeding past. Which one would be harder to stop? The answer feels obvious, doesn't it? But the physics behind why it's so obvious is where things get really interesting.
And here they are, our two examples. On one hand, you've got the truck, huge mass, but a really low velocity. On the other, the cyclist, tiny mass, but moving at a high velocity. This is the perfect way to see that stopping something isn't just about speed, and it's not just about size. It's about how those two things work together.
Okay, so here's the official textbook definition. Momentum is the quantity of motion contained in a body. All that really means is it's a way to measure how much motion an object has, and it takes both how heavy it is and how fast it's going into account.
And physics gives us this incredibly simple and powerful formula to figure it out. P equals m times v. In this equation, P is just the symbol for momentum, m is for mass, and v stands for velocity. It's a direct relationship. If you increase the mass or you increase the velocity, you increase the momentum. It's that simple.
This table really breaks it down perfectly. Just look at the first two cases, an empty shopping cart versus a full one, both rolling at the same speed. The full one has more mass, so it has more momentum. It's just harder to stop. But now, check out the last two. This shows you can get a lot of momentum in totally different ways. A baseball has very little mass, but when it's thrown fast, it has a ton of momentum. And a cannonball? Well, it has so much mass that even moving slowly, it also has a huge amount of momentum. Both of them are going to take a lot of force to stop.
Okay, so now we know the law of conservation of momentum. It just means that if you have a closed system, think of billiard balls on a table with no friction, the total amount of momentum in that system can never, ever change. It can't be created, it can't be destroyed. It can only be transferred from one object to another. The total amount you start with is the exact amount you end with. Period.
So what is a per? Before the balls ever touch, each one has its own momentum. You can add those together to get the total momentum of the whole system. Then, bam, they collide. The first ball slows down, and in doing so, it transfers its momentum to the second ball, which speeds up. And after they've separated, their individual speeds have changed, for sure. But if you add up their new momentums, that total is identical to what it was right at the start.
This is the key takeaway, the elegant truth at the heart of it all. Total momentum before equals total momentum after. And this isn't just for a game of pool. This applies to everything: planets, atoms, and most importantly for our daily lives, cars. All right, let's take this idea.
That's a really important question, right? When you're driving down the road, you and your car have a tremendous amount of momentum. In a crash, all of that momentum has to disappear. It has to go to zero, and it has to do it almost instantly. So how do engineers use this law to protect you?
So to stop, or in other words, to change your momentum, some kind of force has to act on you. But here's the secret sauce. That force isn't just a single number. It's a force that is applied over a period of time. And the relationship between that force and that time is the key to all modern car safety. Take a look at this equation. Force is equal to the change in momentum divided by time. Now, think about a car crash. The change in your momentum is fixed, right? You're going from, say, 60 miles per hour down to zero. That part's not changing. So if you want to make the force that acts on your body smaller, and that's the force that causes injury, what's the only other thing in that equation you can change? You have to increase the time.
And this is where some absolutely brilliant engineering comes into play. Every one of these safety features, crumple zones, seatbelts, airbags, they all have the exact same goal. They aren't some kind of magical force field. They are simply time extenders.
This is it.